reminder where we left off yesterday. So you've already taken these notes, but these are what we're going to have to use as we decide whether molecules are polar or not. Okay. So to determine if a molecule is polar, it said it took two things to be true. First of all, it had to have a polar bond, where we subtract electronegativities, and then it had to be the right shape. It had to be a non-symmetrical shape. That polar is different ends, symmetrical is the same all the way around. So polar and symmetrical are opposites. Same on every side versus opposite ends. So you're either polar or you're symmetrical if you've got a polar bond. So let us look at some molecules and decide, are they polar or not? Is HF polar? Why or why not? So the first thing I have to do is draw the structure so I can see what is hooked to what. If I don't draw the picture, I got no idea. Well, this one's pretty simple. H has 1 dot. Fluorine has 7. Putting the two of them together makes everybody happy. So that's what HF looks like. So I only have one bond in it, and it's the HF bond. Okay. So now I need to look at the numbers. So H is 2.1 and F is 4.0. Because they only need one bond. It only needs one bond. Yeah, H bonds once with F. Okay, we'll go back up there in a second, but I need the 2.1 and the, okay, so let's go back here and we'll see why it only bonds once. Okay. H has 1 dot. F has 7. That's one bond. Okay. Well, and the other thing is H only makes one bond every time. Okay. Now, if H is 2.1 and O is 4.0, the difference, 4.0 minus 2.1, 1.9. What did that tell us about it according to our table? Yeah, if we look at the table, it comes out pretty close to really strong polar. 0.9, the goal was, the limits were, there's our limits. We just got 1.9. 1.9 is right there. It is really polar on the edge of being ionic. They're not sharing fairly at all. Because we've got fluorine, the one that pulls hardest on electrons, with hydrogen doesn't pull back very much. So the electrons are going to be pulled towards that fluorine. Okay, so it's really polar. Okay, and the F is going to be negative, and the H is going to be positive because F had the bigger number. Okay, so it's got a polar bond. Is this shape symmetrical? Does this have a positive end and a negative end? It's got a positive end and a negative end. It's polar. So the answer is this polar? Yes, because it's got a positive end and a negative end. So I got to talk about two things. It's got a polar bond, and there's no symmetry stopping that polar bond. It's not a symmetrical molecule. It's got one end that's negative, one end that's positive. So you talk about both the polar bond and what shape it is. Make sense? Because without both, it can't be polar. Okay, next one, water. Is water a polar molecule? We've got to draw the structure of water. H has 1 dot. It's not, and O is going to be in the middle, so I'm going to put the O with it in the middle. 1, 2, 3, 4, 5, 6. And that gives me a place to hook on the second H. If it's easy to build, I don't do any math. But I real quick check, everything made the right number of bonds. Oxygen made 2, hydrogen made 1. So we got the right number of bonds. So now that I know the structure, the only bond I have to worry about is the OH bond. Is the OH bond polar? Well, I look at O. I had already looked up H, and it was 2.1. O on my table is 3.5. O is got electronegativity of 3.5. I subtract those two, that's a difference of 1.4. Is that big enough to be polar? Yes. So it has a polar bond where the oxygen's negative and the hydrogen's positive because the oxygen had the bigger electronegativity. That's how I knew it was the negative one. Or I could have said, so now that I got a polar bond, I have to worry about what shape it really is. So what shape is this? Well, I've got two atoms hooked onto a center. I only have two choices. They're in a line or they're not in a line. Which one's it going to be? Well, it's going to be bent because of these lone pair. Right? So it's going to be bent. So my molecule is going to look like this. And the oxygen is going to be negative and the hydrogens are going to be positive. So on what side of the molecule is it negative? On the oxygen side, right? What side of the molecule is positive? Hydrogen side. If you talk about different sides with different charges, it's not symmetrical. It's got a top that's negative and a bottom that's positive. One end's negative, the other end's positive. That's polar, because the bent shape can make it polar. Okay, so was water polar? Yep, water was polar too. With the, it actually turns out it goes right up the middle because the two positives on the side cancel each other out. So the charge goes right up through the middle. What about NH3? Once again, the first step is figuring out how to build it. So N with 5 dots, 3 H's with 1 dot apiece can all fit on. No sense doing any math. This is what it's going to look like. So I got to worry about the bond between N and H. Is that bond polar? Well, I looked up the H before and it was 2.1. Now I need to look up N. This table's in your book on page, I think it's only 177. And N was 3.0. Minus 2.1 is 0.9. Was that big enough to be polar? It was from 0.5 to 2. Right? So 0.9 is big enough to be polar. So this is a polar bond. Which one gets the negative? Well, the one with the bigger number, which is the nitrogen. It pulls harder, so the electrons go towards it. Gets a negative charge. And the hydrogen gets a positive charge. Partial positive, partial negative. So your homework tonight's going to ask you to label things like that. The bigger number gets the negative. The bigger electronegativity gets the negative charge. Yeah. We looked at it yesterday, and we said this was the guidelines. Between 0 and 0.4, it's not polar. Between 0.5 and 2, it was polar. Bigger than 2, it was ionic. Okay, so now it's got polar bonds. I got to worry about the shape. Okay. Well, it's got to be a triangle, right? Because I got a center and 3 things hooked. And there's 2 ways that you can make a triangle. You can make a flat triangle, or you can make a pointy triangle. Trigonal planar versus trigonal pyramidal. Which one is this going to be? What would make it a pyramid would be a lone pair of electrons. Nitrogen's got that lone pair. So it's got to be trigonal pyramidal. So my molecule looks like this, where the H's are positive and the N is negative, is that polar? Does it have a positive side and a negative side? Nope, it does. The top is negative, the bottom's positive. Those shapes, bent and trigonal pyramidal, have a top and a bottom. They're not symmetrical. CF4. So the first place we go is to draw the structure. Carbon has 4 dots. That looks like 4 places to hook on fluorine to me. So all the bonds in this are the same. I really only have to check one bond. Is that CF bond polar? Well, F, we looked up earlier, was 4.0. Carbon, on my table, is 2.5. Carbon's 2.5. I subtract 4.0 minus 2.5. Take the absolute value, I get 1.5. Is that big enough to be polar? Yes. So the carbon is the smaller number, so it gets the plus. The fluorine's the bigger number, so it gets the minus. So it has polar bonds. It's met condition number 1. Gotta look at condition number 2. What shape is this? Well, with 4 atoms spread around, there's only one shape, and that is tetrahedral. It's got to be a tetrahedral. So it's going to be this tetrahedral shape. So the fluorines would be on the outside, and the carbon would be in the middle. Does this have positive and negative ends? Where's the positive end? Think about what you just said. The positive end is in the center. Is that possible? Is it possible to have an end in the center? No. My positive is in the center. My negatives are all on the outside. This has polar bonds, but it's not polar. Because its outside's not different. Its outside's the same all the way around. It's symmetrical. The negatives are spread evenly all the way around. So you can have polar bonds and not be polar if you're the right shape. If you don't have polar bonds, you can't be polar. But if you got polar bonds, then you have to check the shape because of this. If this didn't happen, we could just subtract. Life would be good. Okay. But CO2. We've drawn the structure of carbon dioxide a few times. I'm going to go with, I can't picture it in my head, but I'm going to do the right number of bonds. I've got to make it so carbon makes 4 bonds and oxygen makes 2. Since carbon makes the most bonds, it's going to be in the middle. And that gives me carbon with 4 bonds, oxygen with 2 on both ends. I've got to fill in the rest of the dots. And then I should check to make sure that I put the right number of dots. I've got carbon with 4, 2 oxygens, that's 2 times 6 is 12. I should have 16 dots on the screen. 2, 4, 6, 8, 10, 12, 14, 16. There's 16 dots there. Okay, so that's the right structure. That's where you start because you got to figure out what's hooked to what. Okay, now my CO bond. I looked up C before and it was 2.5. I looked up O before and it was 3.5. How far apart are those two? Take the absolute value of it, it's 1. Is 1 big enough to be polar? Oh, yeah, it was right in the middle. We went from 0.5 to 2, so 1 is polar. So this has polar bonds. So it's worth checking the shape. What shape is it? Well, it's 3 atoms, 1 in the middle and 2 connected, and there's only 2 possibilities. They're in a line or they're not in a line. Which one's this going to be? Well, the carbon in the middle doesn't have any lone pair. So the oxygens get as far away as they can, which is linear. So it turns out I drew it the right shape. It is linear. So if I label my oxygen as negative and my carbon as positive, where's the positive charge? Let me ask you where the positive charge on this. What would you say? It's the center. It's not on an end. So this is nonpolar. And what kind of properties are you talking about because of that? Well, we saw water was bent and polar, right? The fact that water was bent and polar is why water is a liquid and carbon dioxide isn't polar. That's why it's a gas in this room. Polar hangs on to each other better than nonpolar. So the reason why CO2 is a gas is because it's nonpolar. It doesn't have any charges. Okay? So that's where the stuff gets used. We can decide what phase it's in because of that. Hey, this does something different. CH3Cl. Would that be polar? Well, carbon with its 4 dots. I can hook on the 3 hydrogens with their 1 dot. And then if I hook the Cl with its 7 dots, it fills everything up. Or I made it so carbon makes 4 bonds, hydrogen made 1, chlorine made 1. Then I had the right number of dots. Okay. So, what kind of bonds does this have? Well, this is different because it's got 2. It's got the CH bond and it has the CL bond. Carbon is always 2.5. H on my table is 2.1. So 2.5 minus 2.1 is 0.4. Carbon's 2.5. Chlorine is 3.0. So if I take that subtraction, I get 0.5. So, is the CH bond polar? No, because it's 0.4. Is the CCl bond polar? So I have 1 polar bond and 3 nonpolar bonds. What shape is this? Well, it's 4 atoms around a center. There's only one possibility. Tetrahedral. So I've got carbon with 3 hydrogens and a chlorine. Right? That's what the shape is going to be. And I know that the chlorine's negative and the carbon's positive. And the other 3 are all neutral. Does this have a negative side and a positive side? Yeah, there's nothing canceling out at the bottom. Right? With the CF4, I had those 4 Fs on the bottom canceling out the one that went up. Here, on the bottom is not canceling out what's happening on top. So this is polar. Look at this. So you got to check 2 things. First, find if there's a polar bond. I didn't do one that didn't have polar bonds because it's kind of trivial. It doesn't have polar bonds, you're done. Doesn't matter what shape it is. If everything's shared evenly, you won't have a positive and negative. Yeah.
So the bonds between C and H are neutral
Because of nonpolar. So the nonpolar doesn't put a positive or negative. Polar puts the positive and negative on there. Does that make sense? Okay. So here's what the book talked about in terms of how you actually detect it. Okay. We said HF was polar. So those are all HFs, and I've labeled the positive and negative ends. The Fs are negative, the H's are positive. This is what we just wrote. Okay. They're randomly arranged right now. But if you take and put them in an electric field, they're going to spin around and line up so that the negative end of the molecule is towards the positive side, and the positive end of the molecule is towards the negative side. And they will line up. Okay? And that tells you the molecule is polar. The fact that they line up. Because it's going to have if it's got a negative end, that negative end is going that way. If I put something that's nonpolar, like that CF4 in between, there's no one side that wants to go towards the positive. All four Fs want to go there, which would mean it doesn't do anything at all because all the Fs want to go that way. Right? And they're evenly spread around. This is how LCD displays work. Okay, ever tried to look at an LCD display when you got sunglasses on? Polarized sunglasses? If you do, if I wear my sunglasses when I'm pumping gas, I'm going to turn my head to the side to read the numbers. Because if I look at it straight on, black. Turn my head, I can read the numbers. That's kind of bizarre. Why does that work? Well, because what you have in that LCD is you have, just like gosh, I forgot what it's called. Find a shot. Those pieces of plastic we looked at to see the colors of fire, the colors, where it had a whole bunch of scratches. Well, that's what the LCDs have it. But behind it, they have long molecules that are randomly arranged, and those long molecules have negative end and positive ends. So they're just randomly arranged before they turn on any electricity. So there's nothing really. So they're lined up behind here. There's no big issue. But then they turn on a field and put the positive here and the negative there, and all of these molecules are now going to line up and fill those spaces in between the lines. And that's why it looks black. Just because those lines have filled up those spaces and not reflecting the light anymore. They block it. You turn off the power, they go random again, and light goes through. What's happening with your sunglasses, polarized sunglasses have those same kind of lines. So if your lines match the lines on the screen, no light gets through. Or if your lines are opposite the screen, no light gets through. But so all the light coming out of here has got to come out like this. So if your glasses are like this, you're okay. But if your glasses are like that, they're going to get blocked, and you're not going to be able to see. So the LCDs work by lining up molecules based on the fact that they're polar. They just line them up. Okay. The reason why I've learned about polar and nonpolar is so we could talk about intermolecular forces. Hey, $5 word. What the heck does it mean? Well, let's just take it apart. Inter. What does the prefix inter mean? You mean between. So it's the forces between molecules. How one molecule affects the molecule next to it. Why we have liquids and gases. So what we've studied so far are bonds. And bonds are intramolecular. Intra means inside the molecule. So that's the bond between carbon and oxygen and CO2. That's intra. Well, we're talking about how one CO2 molecule affects another CO2 molecule. Force between molecules. Okay? Without those forces, we would not have liquids and solids. Gases, what makes something a gas is the molecules don't stick to each other. When it turns into a liquid, the molecules have to stick to each other. And when they turn into a solid, they have to stick to each other better. So without these forces, everything would be a gas. And since everything is not a gas, there has to be something holding these molecules together in the solid and in the liquid. And it's not a bond. It's because the H2Os are still separate. What hangs one H2O onto another H2O in water? There are actually three kinds. The first two get hooked together into one category. That category is called van der Waals forces. Capitalization is a little bit strange on van der Waals because it's a title. Van is like count in Dutch. Der is like de. So van der Waals means count of walls. Waals is a county in the Netherlands. They spell walls pretty strange too. 2 A's and an L. It's a Dutch name. There are two kinds. Dispersion forces and dipole interactions. One of these is easy to understand. One of them is a little bit more complicated. So we're going to do the easy to understand one first. The easy to understand one is dipole interactions. Dipole, prefix di, two, pole, two-pole interactions. How the pole on one molecule affects the pole on the next molecule. So dipole interactions means you have to have two poles, which means you have to be polar. If you're not polar, you can't have two poles. So you can't do this. So two-pole interaction. The pole on one molecule interacts with the pole on another molecule. The negative on HF would be attracted to the positive on another HF. That's a dipole interaction. That those two poles would interact. So the partial negative on one side hangs on to the partial positive on the other side. Why would the two poles attract each other? Because positive and negative and opposites attract. Yep. I told you dipole interaction is pretty easy to understand. So this is why we figured out why we need to figure out if it's polar or not, so you can figure out whether to do this. If you can do this, it can stick together better. But it's not a bond. It's just an attraction. It's what happens when it's what I have to break when I boil water. Water liquid to water gas, that's boiling water. That's the intermolecular force. If I tear water apart into hydrogen and oxygen, then I'm breaking bonds, real bonds. These are much, much weaker than real bonds. Okay. Makes sense? This is why we're figuring out if they're polar, to figure out if they can do this. If they can do this, they stick together better. So this is what a liquid really looks like. You got a whole bunch of positive and negatives all interacting with each other as they move around. When you cool it down enough, they're going to line up in a pattern, and you'll have a solid. Okay? Everybody okay with dipole interactions? Okay. So if I got opposite charges, they're going to attract and they're going to stick together a little bit better. Okay. Dispersion forces. This one's a little bit harder to understand. And it's hard to understand because we can't see, it's still opposites attract, but where do they get the opposite charges? Okay. So, where did I put it? Ah, yes. Here it is. So I have a balloon. I had one. Bizarre, it's got smiley faces on it. Sweet. Okay, so I got a balloon. Does this balloon have a charge? Does the wall have a charge? So the balloon doesn't stick to the wall. Everybody okay with that? But if I take a balloon and rub it on my hair, what I'm doing is rubbing electrons off of my hair onto the balloon. So my hair gets a positive charge and the balloon gets a negative charge. And they're opposites and they attract. Does the balloon have a charge? Now the balloon has a charge. Everybody agree that now it has a charge. Does the wall have a charge? Okay, so how the heck is that balloon staying there? If the wall had a negative charge, a positive charge, it would make sense, wouldn't it? Well, the balloon's sticking. Somehow that wall has to have a positive charge. Can't figure out how. Well, I know how. But everybody know how we can tell right now that wall has a positive charge. Because the balloon is sitting there. All right, so how do we get there? So, luckily for me, they put together a simulation so I don't have to explain it in lots of words. Okay, they're showing a sweater. A sweater is not my hair, it's the sheep's hair. It's wool. Okay, so it's just hair in a balloon again. And there's the wall. So I got hair, I got balloon, I got wall, I got all the things that we talked about. Okay? So if I take the balloon and rub it on the sweater, it steals the electron away from the sweater, and the balloon gets a negative charge, and the sweater gets a positive charge, and the balloon sticks to the sweater. Just like the balloon would have stuck to my hair. Okay? So everybody's okay with this because they have opposite charges. Over here, the wall has equal numbers of positive and negative pieces. It's neutral. But remember, only one of those pieces can move. Positive, the nucleus stays in place. Electrons can move around. So when I bring my balloon towards the wall, it pushes the electrons out of the way. And then right next to the balloon is a positive charge. And the balloon is negative. So that balloon's going to stick to the wall. That's what's holding up that balloon. The big charge on the balloon pushed the electrons and the bricks away. So I got positive next to negative and they stick together. No, it's not dipole because it's not permanent. As soon as I take this balloon away, those electrons come back. My wall never got a charge. Okay. So this is what dispersion. This is how dispersion forces work on a smaller scale. You don't have full balloons. You got molecules. But the charge on one will affect how the charge is distributed on the other. I can move electrons around on the wall by bringing the balloon next to it. Okay? That's dispersion forces. And we don't have to move things around because electrons are moving randomly. So that in your molecule, for some fraction of a second, the electrons are going to be more on this side than on that side. Fraction of a second later, they'll be back. But for a fraction of a second, momentarily, I think is the word the book used, right? Momentarily, those electrons are going to be more over here than over here. They're going to have temporary partial charges. Again, the book called it a momentary dipole. So it's not a permanent one. It's just random motion brings more electrons over here than over here. So one end is temporarily negative, the other end is temporarily positive. Temporarily partially negative and temporarily partially positive. And the negative and positive charges are going to affect the molecules next to them. Now, when you have electricity that flows and you move charges, that's called conducting. When you move electrons around without ever actually moving them, like I moved the electrons in the wall, but as soon as I came back, they came back, and I didn't actually touch. If you can move the electrons around without touching, that's called inducting. Not conducting, inducting. So this is called an induced charge. To make happen without doing it directly. That's what inducing means. So the charge on one molecule affects the molecule next to it and gives one into charge. If I got a negative here, it's going to push the electrons away. And so they're going to be momentarily attracted. Okay. We'll look at that more tomorrow. But homework esta noche is that. Have a pleasant afternoon.